Hello everyone, my name is Yifan. Welcome to my talk. And this talk is a longer version of the previous talk, also in the talk list of the Symposium in Fields Institutes. If you didn't have enough time, you can turn to look at that short video to get the main ideas of this talk. And if you are more interested, here I will explain you more about the details of this paper. And the title is Consistency of Hierarchical Parameter Learning, Empirical Bayes and Kernel Flow Approaches. This is joint work with Andrew Stewart and Humel Wadi at Caltech. The following is one page's overview of our work. We are in the context of supervised learning, or in the statistics language, is non-parametric regression. To solve this problem, we use a popular approach, the Gaussian process regression, or Kernel methods. In this method, the question we are focusing on is how to select kernels based on data. And as all we know, there are some hierarchical parameters in the kernels, and we want to learn these parameters from data. To learn these parameters, we consider two different algorithms. And one is from probabilistic perspective, is a Bayes approach, and especially we use empirical Bayes. Another one is more approximation theoretical. And this is a recent method proposed by Professor Humel Wadi, and it's called Kernel Flow. For the two different algorithms, the contribution in this paper is that in theoretical parts, we provide some theoretical analysis of the consistency of the two different algorithms for Matern class model. And we characterize the selection bias for different algorithms in learning the parameters. Experimentally, we go beyond the Matern class model. We test other well-specified model. We look at their behaviors. Also, we consider the model misspecification to look at the robustness of the two algorithms with respect to the model errors. That is a basic overview. And to get it started, we first give a reminder of Gaussian process regression. And we are solving the supervised learning problem, or in other language, in statistics language, we are doing a non-parametric regression, or in numerical analysis perspective interpolation. We want to recover your dagger from its pointwise values, yi equals your dagger xi, I from 1 to n. Here we assume the loess-free scenario, so we didn't have loess in the observations to keep it simple. And the popular GPR solution, or Kernel method, solves the problem in the following way. First, we give some notations, and the theta is a hierarchical parameter in the kernel family. K theta being a kernel function, it is defined from d times d to r. And we use a capital green x as a collection of all data points, x1 to xn. We use u dagger x to mean u dagger applied point-wise, component-wisely to x, so that this is a vector of dimension n. Similarly, k theta xx will be a matrix of dimension n times n. K theta dot x will be a collection of functions with entry k theta dot xi. Finally, the GPR solution u dagger or u dot theta x will be given in the following form. This should be very familiar to you if you have some experience in GPR or Kernel method. And usually there is also some logit, and you plus some gamma times some identity matrix if you have loess. But here we are doing the loess-free scenario, so this will be the final solution. It depends on three important things: the kernel k theta, the theta is a hierarchical parameter, the data location x, and the ground truth u dagger. Those three different things are very important, and so we use different colors to highlight them. That is Gaussian process regression, and it has many favorable properties. For example, for any theta in the parameters, it will give us an interpolated solution on x. That means the GPR solution will agree with the ground truth u dagger on all the training data points. In machine learning language, we are easily achieving zero training error. So this is not hard. But however, in practice, and people care more about out of sample error or the generalization error. In this case, the question is that how shall we pick a good theta? This is a model selection problem, so we need to learn the hierarchical parameter theta from data. To solve this model selection problem, the roadmap of this talk is as follows. First, we discussed two different approaches for it, the Bayes approach and the approximation theoretical approach. Then we compare the performance, especially their consistency as the number of data goes to infinity and beyond, and focus both on theoretical parts and the experimental parts. We begin with the Bayes solution. So the Bayes solution is to put everyone in probabilistic way. So we want to select theta. So naturally, we put a prior on theta, and we assume our U dagger is drawn from some Gaussian process model. Under this probabilistic model, we can calculate the posterior. If we adopt the empirical Bayes perspective with an informative prior, we will get a point estimator for the parameter theta, which is given as a minimizer of the EB loss function, which is defined as follows. It is lective log likelihood of some Gaussian measures with covariance k theta xx. Essentially, we are doing maximum likelihood estimates. The EB solution is just to select theta being the theta EB, and it depends on two things, the green x or data points and the truth U dagger. That is the Bayes solution. Then we move to the second approach, the approximation theoretical approach. So as we have seen, in the Bayes solution, we assume theta U dagger to have some prior distribution. This assumption may be brittle to model misspecification because this probabilistic assumption is very strong. Alternatively, we can do something more straightforward. Suppose we want some target cost D, we want the solution, the GPR solution to be close to the ground truth U dagger in this cost. Under this criteria, the natural way to select theta is to select the one that optimizes the distance between the ground truth and the GPR solution. This is quite ideal and natural. However, U dagger is not available, so our solution is to use approximation. As one example, we can turn to optimize the distance between the GPR solution using X and the GPR solution using a fraction of the dataset pi x, where pi is the subsampling operator, pi x will belong to X. And this perspective is very similar to the method of cross-validation because we are using the fraction of the dataset pi x to infer the property of the previous dataset X. Here, we are especially interested in a specific choice of D, and that is originated from the work of kernel flow by Owadi and Yu in 2018. And they have some extensions of this method to training neural networks layer by layer in 2020. Also recently, Hamze and Owadi use this method to do dynamic system learning. The KF loss, KF estimator is given as follows. It's a minimizer of the KF loss, which is defined in this way. It's a distance between the two GPR solutions in the sense of the k theta norm. K theta norm is the RKHS norm because for each kernel k theta, there will be a reproducing kernel Hilbert space and you have a well-defined norm. The KF loss compare the two solutions in this norm and normalized by the norm of the first one. We can interpret the KF loss as follows. A kernel is good in this loss function if subsampling data does not influence the GPR solution much in the sense of the k theta norm. This is very natural. Okay, so those are the two different approaches that we are interested in. Then we go to analysis parts. We want to say how they perform. Our first question is very simple. And how do the two different estimators behave as the number of data goes to infinity? This is a consistency question. And we will answer this question for some specific model of U dagger, theta, and X. To begin with, we specify the setting for our model. We are doing the Matern regularity model, but on torus rather than on the whole domain, so it's quite different. The domain D equals TD, T is a torus, so it's 0, 1 to the power of D, but with periodic boundary. The setup for our data is on an equidistributed lattice on the torus with step size 2 to minus q. So the total number of data is 2 to q times d. The kernel family we are considering here will be minus Laplace to the power minus t. This is the Matern class model on a torus, but only with one parameter, the regularity parameter. Most generally, we also have the amplitude parameter, sigma square, and length scale parameter, sigma and tau square here. We will discuss these possibilities in the end of this work. And here in our theoretical part, we focus on the regularity parameter. And also to define the kf loss function, we need a subsampling operator, pi. Here we choose the pi that maps an xq, the q level lattice to q minus 1 level lattice. In numerical analysis perspective, this is just the one level grade coarsening. We go to one level of grade to another level of grade. Under this setup, in our paper, we have the following theorems. Informally, this says that if we have a model for your dagger, it's drawn from n0 and with covariance minus Laplace to the power minus s. Then, as the number of data goes to infinity, we have a well-defined limit for both estimators. For the empirical Bayes estimator, it will convert to s, while for the kernel flow estimator, it will convert to a very interesting limit, s minus d/2. The convergence is in probability. Here, we will not elaborate on the proof of the theorem. We mentioned that the analysis is mainly based on the multi-resolution decomposition, and we use some short complements technique, and that is appeared in Professor Wadi's work of gauntlets. We also use some probability, the uniform convergence of random series to conclude the convergence of minimizers. Though we didn't talk about the proof in this talk, we will talk about some experiments to convince you the correctness of the theory. How does it work in practice? We consider a one-dimensional example, and we choose S2 to be 2.5. The number of data is 2 to the 9, and we use match size 2 to the minus 10 to discretize the Laplace operator. The following, for a single realization of your dagger from this Gaussian process, we draw the figures of the loss function for the two different methods. In the left-hand side is the empirical loss. The x-axis is the value of t, the parameter value, and the y-axis is the loss function value. We can see that the minimizer is 2.5, matching the prediction because s equals 0.5. In the right-hand side, we say that the minimizer of the kf loss function is 1, matching the prediction because we predict it will converge to s minus d/2. Here is 2.5 minus 0.5/2. That is exactly 1. Moreover, we can see some patterns in loss function. For example, in the EB loss, we see that the loss function decays linearly and before the 2.5 and then blows up very quickly. For the kernel flow, it has a more symmetric behavior. Our theory in the paper can completely predict those behaviors. Okay, so hope I have convinced you the correctness of this theorem. Then we move to our next question, which may be even more interesting and important. That is, we have different algorithms. Okay, we have their consistency, but how are the limits special? Because we have two limits, 2.5 and 1. This is related to the implicit bias of different algorithms in learning parameters. To answer this question, our strategy is look at the L2 population error of the different parameters. In our first experiment, we select the number of data to be 2 to the q, and we compute the L2 generalization error between the ground truth and the GPR solution. And to make the figure nicer, we average this one with respect to the Gaussian process your dagger is drawing from to make this loss function deterministic. And we compute this quantity for various t and q. The following is the output. The x-axis is the value of q, that means the logarithmic number of data. And the y-axis is the average L2 generation error. For different t, we plot the tendency of the loss function with respect to q. We see that for different t, the L2 generalization error will decrease as the number of data increase. That is quite natural, but converging to the ground truth. And interestingly, when t move from 0.5 to 1, the slope of the convergence becomes sharper. That means the convergence rate becomes better. However, when t goes beyond 1, the slope rarely changes. That means the convergence rate saturates. So t equals 1 will correspond to the minimum t that suffices for the fastest rate of L2 generalization error. And remember that t equals 1 is the parameter that kernel flow will pick. So that implies the implicit bias of kernel flow algorithms. We also do another experiment. We fix the value of Q to be 9, and we still compute the same quantity, but we only vary the value of T. And following the figure, the x-axis is T, y-axis is the L2 generalization error. We see that in this case, the minimum error is achieved by 2.5, and 2.5 is a parameter that EB will select. So in this case, this implies the implicit bias for EP algorithm. It will select the T that achieves the minimum L2 error in this average things. Let's do a summary of our theory. So for Matern-like model on a torus, we have theory to prove the convergence of the two different algorithms in the large data limits. Moreover, we observe numerically that EB and KF have very different selection bias. For EB, it will select the T that achieves the minimum L2 error in expectation, while kernel flow will select the minimum T that suffices for the fastest rate of L2 error. So they are quite different and they're quite interesting. Our work provides more detailed discussion of this phenomenon and provides some characterization of those different bias. Okay, that is pretty much for the theoretical part of Matern-like kernel. So one would naturally ask that, how do the theories extend beyond the Matern class model? And so to answer this question, we use the power of numerical experiments to investigate more about the different algorithms in other models. This goes to our second part. We will discuss the experiments beyond the Matern models, and we also include the model misspecification that is very interesting and useful. But first, let us complete the story for the Matern class model. As before, we mentioned that we only consider the regularity parameter. Now we choose the more complete characterization. And this is the Matern class model on a torus. We have 3 parameters. Sigma is the amplitude, tau is the length scale, and S is the regularity. And we want to say that how the two different algorithms behave for learning the 3 different parameters. We conduct experiments for D to be a torus, but with 1 dimension. And here we didn't present the details of the experiments, the figures. If you want to look at the figures and all the setup, you can look at our paper. We only give a short summary of our discovery. We found that empirical Bayes can recover both S and sigma respectively or simultaneously. Respectively means that, for example, S is fixed and it can recover sigma. Simultaneously means that both the 2 parameters are unknown and you do joint optimization to recover them. But in the 1-dimensional case, it cannot recover tau. And this is not surprising because a general guiding principle to look at the consistency of empirical Bayes or maximum likelihood is to look at the mutual singularity of the Gaussian measure in the infinite limits. So if we, in a 1-dimensional case, if you change sigma or S, the Gaussian measure will change to a completely mutually singular Gaussian measure. So that's why it can be recovered in the infinite limit data limits. However, in 1-dimensional case, changing tau only leads to equivalent Gaussian measures, so we cannot consistently recover tau. However, if we have a large dimension, for example, larger than 3, then change of tau will also correspond to mutually singular Gaussian measures, and we expect that it can also recover tau in this case. And for the approximation theoretical approach, kernel flow, we say that it can only recover the S minus D over 2 over 2, but not sigma and tau in our experiments. Okay, so that is the result for the general Matern class model on the torus. And another very natural question for this Matern class model is that we have theory and experiments for the recovery of regularity parameter S. And a natural question is, you have 2 algorithms, right? But and how they compare with each other. So what's the variance, for example, the simplest question? To answer this question, we still focus on the same setup. We use one-dimensional case, and we choose S to be 2.5. We use the number of data to be 2 to the 9, and we compute the normalized variance of the two different estimators. And we see that the variance of empirical Bayes is much smaller than the variance of kernel flow. So that means if we are doing this well-specified model, the Matern class model, we need to choose an empirical Bayes because it will lead to an estimator that has better variance. I think this phenomenon is not that surprising because in statistics, people usually think that the maximum likelihood will have optimality in terms of the optimal variance among a lot of models. Okay, so that nearly concludes our Matern class model part. And here we will investigate other well-specified models. For our first example, we'll assume U dagger is drawn from this Gaussian process. Here is no longer the minus Laplace, but a general elliptic operator. We're still doing in one-dimensional case. And here, A, we choose it to be a discontinuous field function. It has a discontinuity point at 1/2. Because it's a well-specified model, so we choose the case theta to be the same kernel as a covariance function. And we choose the data position x to be the uniform lattice as before with number of data 2 to the 9. Interestingly, we found that in this case, the behavior of empirical Bayes and the KF is similar to the Matern class case. They converge to the limit s and s minus d/2. And we calculate their variance. We see that as before, the variance of EB is much smaller than the variance of KF. So in this case, if we just change the minus Laplace to this elliptic operator, the conclusion didn't change much. Then in our second example, we consider the U dagger, the ground truth, is drawn from some stochastic partial differential equations. And here, the left-hand side is an elliptic operator with coefficient a 1/2, and a theta is defined in the following form. And it has discontinuity points parameterized by theta. And the right-hand side is a Gaussian process with mean 0 and the covariance minus Laplace to the power of -1. And essentially, U dagger is a Gaussian process with the following covariance function with s equals to 1. So in this well-specified model, we will choose our kernel model to be the well-specified one, but with the theta to be an unknown parameter to be inferred. We choose the same setup for the data location. Then we use EB and KF to recover the discontinuity points. Experimentally, we found that both EB and KF will recover the discontinuity point theta equals to 1/2. That's quite ideal. Okay, that is for the model well-specification part. Then we will go to the model misspecification. For our first example, we consider the U dagger is drawn from the Gaussian process with this elliptic operator and with the same as before. However, because now we are doing the model misspecification, so the kernel family we are using to define the estimators is no longer the same as the covariance U dagger is drawn from. Here we just assume it's a Matern class. So there is a mismatch. And X is still uniform lattice with 2 to the 9 number of data. Interestingly, we found that even in this model misspecification setup, the empirical Bayes and the kernel flow will still converge, and the behavior is very similar to before. So it converges to S and S minus d/2. However, the variance behaves differently. And if you remember the previous results, we see that the empirical Bayes has a much smaller variance compared to kernel flow. However, now their variance is similar in magnitudes. This means that empirical Bayes loses this priority in variance in this model misspecification part. That means that empirical Bayes may have some weak robustness with respect to the model misspecification. In our second example, we consider a counterpart of our well-specified model. We consider U dagger is drawn from stochastic partial differential equations and with set up as before. But for the kernel k theta used to define the estimators, we didn't use the previous one. Previous one choose s equals to 1 so that it's well specified. However, here we choose s equals to 5, so it's not well specified. And in this case, if we solve the dB and kf estimator, we will find that kf still recovers theta equals to 1/2, but EB fails to give a meaningful limit. This means that in this model misspecification part, the kernel flow will have a better robustness compared to EB, because kf still succeeds in learning the discontinuity points, but EB didn't in this model misspecification part. Our final example for this model misspecification is a different one. And here, the model misspecification is coming from the deterministic model. So remember before, we always assume U dagger is drawn from some Gaussian process. But here, for this example, we assume it's not drawn from a distribution, but it's a solution to a deterministic PDE. Still, we are doing the one-dimensional case. The right-hand side is a Dirac function. So essentially, U dagger is a green function and of this differential operator. And using this U dagger, we use a Matern class model to define the EB and KF estimator, and we still assume the uniform lattice of the data points with total number to the line. And we can use this data to define our estimators and compute the estimators numerically. Interestingly, even in this deterministic setup, we found that the experiments show EB will recover 2s as the data goes to infinity, while kernel flow will recover s. So it's very interesting that even in this setup, we have some sensible limits. And in our paper, we have some discussions on why this is achievable. And the reason comes from the theoretical regularity of this U dagger, because when U dagger is drawn from some Gaussian process, we can prove the convergence of the estimators. In that case, one property we rely on crucially is the theoretical regularity of the Gaussian process. And if you are interested, you can look at our paper to know more details about this experiment. Okay, so that is pretty much the whole thing of this work that I want to talk about here. And here are some takeaway messages. First, theoretically, for Matern kernel model, we can prove the consistency rigorously about EB and KF in the large data limits, and they have very different selection bias. EB will select the T that achieves the minimum L2L in expectation, while KF selects the minimum T that suffices for the fastest rate of L2L. And we have also many numerical comparisons between the two different algorithms. We go every parameters in the Matern class model, and then we consider the variance, and that is generally a very sensible observable for different estimators. We consider the robustness to model misspecification. This is quite important because practically, I believe that most models have errors, so you need to know whether your model is sensible to those errors. We also have a very short discussion in this paper about their computational cost. Generally, in this work, we are mainly doing hierarchical parameter learning in this Gaussian process scenario. And there are two different approaches: the Bayes approach, which is probabilistic, and the approximation theoretical approach, which is more frequentist and more deterministic. Those two different algorithms have very different principles, and they lead to very different behaviors. The general question we want to solve and we are interested in is to characterize their selection bias and characterize their behaviors in many different models. For example, and not only in those Matern class, the ideal model, but also in more complicated and practical machine learning models or immerse problems to explore their advantages and disadvantages. We believe those kinds of contribution will make the users easier to choose different algorithms when dealing with different model misspecifications. Yeah, that's it. I'll thank you for your attention.